Come on dears, let us proceed further in chapter number 1, today's 4th lecture. Please kindly read the statement of illustration number 8. Come on, have you read it? Tell me, what is asked to find out the expression of self-inductance of a solenoid? Very simple. Look, what was the symbol for self-inductance? Capital L. What was the formula from basic definition? It was capital Phi upon capital I. Fine. What is capital Phi? It is total magnetic flux linked with a solenoid having capital N number of turns. And what is the formula for that magnetic flux? NBA cos theta. Fine. NBA cos theta, where theta is angle between vector A and vector B. Whenever magnetic field is produced inside the solenoid, the cross section of solenoid is perpendicular to magnetic field. That's why theta angle is 0 degree, and that's why I am writing theta equals to 0 degree. Fine. Upon I as it is. Come on, capital N as it is. What about capital B? The magnetic field produced inside current carrying extremely long solenoid. Remembered from 3rd semester, it was mu 0 Ni, where it is small n, mu 0 Ni, mu 0 Ni, correct? And into A cos 0 degree is 1 upon I. Come on, I ones are I getting cancelled. Now n as it is, mu 0 as it is. What is small n? What is small n? Number of turns per unit length. That is total number of turns divided by total length. Come on, total number of turns is capital N, total length is L into A. Fine. And now this is mu 0. Come on, n into n, that is n square into A upon L. Mu 0 n square A upon L. Simple. For a given solenoid, remember these three values are constants. So now, if you think of relation between capital L and capital N, then that relation would be L proportional to n square. L proportional to n square. Remember, self-inductance of a solenoid, of course, extremely long solenoid, is directly proportional to square of total number of turns. Fine. And if it is direct proportionality relation, then you know L1 upon L2 equals to N1 square upon N2 square. Direct proportionality, then 1 to 1 2. Speak out. 1 to 1 2. So L1 upon L2 is equal to N1 square upon N2 square. Now same result we are going to use in the exercise of this chapter. Okay, please remember this. Fine. Now we go ahead in the theoretical part. Let us study one very important short note. The title is mutual induction. Mutual induction. This is also one phenomenon in which EMF is induced. I am showing you how. My dears, remember in case of self-induction, we had considered only one coil. But here we are going to talk about mutual induction. So we are talking about two coils which are kept near to each other, which are kept close to each other. Fine. Say this is coil number 1. This is coil number 1. Correct? Coil number 1. Say this is coil number 2. This is coil number 2. Fine. Now can you see in the figure? Coil number 1 is connected across, come on, rheostat, battery and key. Coil number 2 is connected across sensitive galvanometer. Fine. Now when we press this key, what will happen? the path will be closed, and through this closed path, when current is passing, that current would produce its own magnetic field. Fine. And the magnetic field lines of that magnetic field I have shown in the diagram. You can see all the magnetic field lines are definitely passing through coil number 1. That is true. But because coil number 2 is very close to coil number 1, you can see the diagram. Out of this many field lines, some field lines are passing through second coil also. And because of that number of magnetic field lines which are passing through second coil, you can say now second coil has got some magnetic flux. Okay. What has happened here? You are passing current through first coil, and what is the, who is affected here? You are passing current through first coil, and thereby coil number 2 is affected. Coil number 2 is affected. दिया इधर जलता है, धुआं उधर से निकलता है. दिया इधर जलता है, धुआं उधर से निकलता है. I mean to say there is some relation between coil number 1 and 2. That sort of relation only is known as mutual induction. My dears, remember, not necessary that you should pass current through only coil number 1. Not necessary. If you desire, you may pass current through second coil, and at that time you can talk about magnetic flux linked with coil number 1. I mean to say, when two coils are placed near to each other, through either coil when we are passing the current, the rest coil gets some magnetic flux. Okay, fine. Now, using Biot-Savart's law, which you had studied in semester 3, we can prove here that magnetic flux linked with second coil is directly proportional to current passing through first coil. As this current goes on increasing, this magnetic flux increases proportionally. Fine. Phi 2 proportional to I1. Phi 2 proportional to I1. Remove sign of proportionality, put some proportionality constant. It is none but M21. M21 into I1 as it is. You know what is M21? It is coefficient of mutual inductance, or simply mutual inductance of second coil with respect to first coil. Fine. The way you have written here phi 2 proportional to I1, you may write phi 1 proportional to I2. Phi 1 proportional to I2. And at that time, if you remove sign of proportionality, if you put proportionality constant, it is M12. It is M12. Come on. How would you remember this? Very simple. Double 2, double 1, double 1, double 2. Come on. Double 2, double 1, and here double 1, double 2. Okay, fine. Now find out M21 from here. Find out M21. It will be phi 2 upon I1. Come on, M21 is phi 2 upon I1. Similarly, if you want to find out M12, it will be phi 1 upon I2. Come on, phi 1 upon I2. Fine. And now tell me, what about unit of this? Unit of mutual inductance. Come on, unit of magnetic flux is Weber. Unit of current is ampere. This Weber upon ampere is known as Henry. Is known as Henry. And Henry symbol is capital H. So, last time also we had studied about unit of self-inductance. It was also Henry. So, remember, whether it is self-inductance or mutual inductance, the unit remains same. SI unit is Henry. Fine. What about definition? Come on. Let us define this mutual inductance from this formula. Just to make the denominator, you just make the denominator 1 unit. Take I1 equals to 1 unit, and then you will get M21 equals to phi 2. Out of two coils which are kept very close to each other, if current passing through any one coil is 1 unit, then magnetic flux linked with rest coil or with second coil is known as mutual inductance of those two coils. I repeat, out of two coils placed near to each other, the magnetic flux linked with either coil because of unit current passing through another coil is called mutual inductance of those two coils. I repeat, out of two coils which are placed very close to each other, comma, magnetic flux linked with either coil because of unit current passing through another coil is called mutual inductance of those two coils. Fine. Come on. In case of mutual induction also, remember Faraday's law on electromagnetic induction holds good. So let us use that law. Come on. What was that law? Mathematical form was E equals to minus d phi by dt. Instead of E I am putting here E2. Instead of phi I am putting phi 2. Come on, E2 equals to minus d phi 2 by dt. So it is now minus d by dt of phi 2. Come on, minus d by dt of phi 2. What is phi 2? What is phi 2 from here? Come on, M21 I1, M21 I1. Here it is, M21 I1. But because for the given arrangement of two coils, this M21 is constant, I can take it out. Come on, take it out of the symbol of derivative, and then left is di1 by dt, di1 by dt. Fine. And now avoid this negative sign just because we want to define. Come on, make subject of the equation M21. Avoiding negative sign, if you make this as subject of equation, M21 will be E2 upon di1 upon dt. E2 upon di1 upon dt. Now again we would like to give definition. Let us see now second definition of mutual inductance. If di1 upon dt is 1 unit, then what will happen? If this is 1, then M21 will be equal to E2. M21 will be equal to E2. How would you define now? Out of two coils placed near to each other, the induced EMF develop in second coil because of time rate of change of current passing through first coil equal to 1 unit is called mutual inductance of those two coils. I repeat, out of two coils placed near to each other, the value of induced EMF develop in either coil because of 1 unit rate of change of current through another coil is called mutual inductance of those two coils. Fine. Now here in the next example we will prove that this M12 and this M21 both of them are equal. Come on, M12 is equal to M21. When both of them are equal, we can write common symbol for that. Let it be capital M. You know what is this? Mutual inductance of first coil with respect to second coil. This is mutual inductance of second coil with respect to first coil. And when both of them are equal, let them be shown by symbol capital M. Okay. This very result is known as, remember, it is called reciprocity theorem. Reciprocity theorem. We will prove this in next example. Okay. Now let us talk about on which factors value of M depends. See, value of capital L, self inductance, remembered it was depending on 4 factors. Same 4 factors you have to write here also, but in case of self induction we were talking about only 1 coil, and here we are talking about 2 coils. So all those 4 factors you have to think for both the coils. Say number of turns of both the coils, say shape of turns of both the coils, size of turns of both the coils, and also type of medium used as a core. Core means the medium which is present at the center around which the winding is done. Okay, fine. Then one more factor, it also depends on distance between the 2 coils and relative orientation. Orientation means setting or arrangement, setting or arrangement. You may think of 2 coils which are parallel to each other, you may think of 2 coils perpendicular to each other, or it may have any other angle between them. So in space they might be arranged in different ways. Depending upon different orientations, the value of capital M is different. Okay. Now come on, read this statement of illustration number 9. Read it? Look here now. In textbook, they have not drawn a figure. You will find the things a bit difficult. You will find all the things very easy, provided you understand this figure. Look here. Consider two coaxial solenoids. Coaxial means having same axis of same length, and that same length is L. Okay? Come on. This is smaller one and this one is bigger one. The cross-sectional area of smaller solenoid I am taking as small a. Mind well, small a is not radius. No, no, no. It is cross-sectional area of smaller solenoid, or you can say cross-sectional area of common area of intersection between small and big solenoid. This much is the area of intersection, common area in both the solenoids. Okay. Now tell me, consider small solenoid as solenoid number 1 and big solenoid as solenoid number 2. If you pass I1 amount of current through small solenoid, naturally inside small solenoid you will get magnetic field. Let it be B1. Don't you know formula of magnetic field inside the extremely long current carrying solenoid? In third semester you have studied B equals to mu 0 n I. Fine. That's why I am writing here B equals to mu 0 n I. Everywhere I should write 1. B1 equals to mu 0 n1 I1. What is this small n1? Number of turns per unit length in first solenoid. Okay. It is nothing but capital N1 upon L into I1. Fine. And now tell me, because you are passing current through the winding for small solenoid, you are going to get magnetic field inside the small solenoid. Okay. My dears, this is the symbolic presentation of winding. Can you recognize? These dots indicate those turns which are coming out perpendicularly from the plane of the figure. And these cross symbols, they indicate magnetic field lines entering the plane of the figure perpendicularly. Dot for coming outside, cross for going inside. From upper side they are coming out, from the lower side they are going inside. Got it? This way. Winding is made this way. Winding is made this way. Okay, fine. Now tell me, because you are passing current in the winding of small solenoid, you can expect magnetic field in the small solenoid. And that I have shown with the green color. Okay. That green colored magnetic field lines, they pass through only this much part which has area A. Come on. Now, out of complete cross section of second solenoid, that is big solenoid, only this much part has magnetic flux. Let it be phi 2. And magnetic flux linked with a second solenoid, it is phi 2 equals to, by formula remember, N2B1A. N2B1A. When you are going to find out the magnetic flux linked with second solenoid, here you should take total number of turns in the second solenoid. Here magnetic field of first solenoid. Okay. Because we are going to discuss about mutual induction, when you are talking about magnetic flux linked with second solenoid, you should think of magnetic field produced in the first solenoid. So here phi 2, but here B1. Fine. N2 as it is. What is B1? B1 is mu 0 N1 I1 upon L. Mu 0 N1 I1 upon L into small a. And now take this I1 in the denominator. So phi 2 upon I1. Come on, phi 2 upon I1. It is mu 0 N1 N2 A upon L. Mu 0 N1 N2 A upon L. Okay. But what is phi 2 upon I1? Phi 2 upon I1. Phi 2 upon I1 is nothing but M21. Fine. Now come on, phi 2 upon I1 is nothing but M21. This right hand side as it is, give it equation number 1. And now, take a big solenoid as solenoid number 2. If you pass I2 amount of current through the winding of second solenoid, you can expect magnetic field inside second solenoid, and by symbol it is B2, by formula mu 0 N2 I2. What is small n2? What is small n2? It is number of turns per unit length in second solenoid, okay, and it is by formula total number of turns in second solenoid divided by total length. Fine. Now, because of magnetic field produced inside the big solenoid, out of that, how much is the magnetic flux linked with the small solenoid? Let it be phi 1, okay. The way you had written here phi 2 equals to N2 B1A, similarly we can write here phi 1 equals to N1 B2A, N1 B2A. Remember, here it is phi 1 means magnetic flux linked with a small solenoid. Then here total number of turns in the small solenoid. But when you are talking about mutual induction, if here magnetic flux of first solenoid, you should take magnetic field of second solenoid, that is B2, correct? And here also small a. Why? Tell me. When you pass current in the winding of second or big solenoid, you can expect magnetic field inside big solenoid, which I have shown in the figure with yellow colored magnetic field lines. Now tell me, do you find all these yellow colored magnetic field lines, they are passing through small solenoid? No. Out of this whole number, only certain yellow colored lines are passing through small solenoid which has cross section small a. So that's why I am writing here also small a. Mind well, in both the cases you are supposed to write common area of intersection, and common area of intersection between first and second solenoid, it is the smallest area, it is the cross sectional area of small solenoid which is small a. Fine. N1 as it is. What about B2? B2 is, come on, mu 0 N2 I2 upon L, mu 0 N2 I2 upon L into A. And now take this I2 down. So it is phi 1 upon I2, and that will be mu 0 N1 N2 A upon L, mu 0 N1 N2 A upon L. What is this? Phi 1 upon I2. Phi 1 upon I2. Phi 1 upon I2 is how much? M12. So let me write here. This is nothing but M12, correct? Right inside as it is, give it equation number 2. From equations 1 and 2, we can make out when right hand sides are same, left hand sides will be same. So M12 equals to M21. Come on everybody, M12 equals to M21. Whatever is the mutual inductance of first coil with respect to second coil, same is the mutual inductance of second coil with respect to first coil. This both the values are equal, so let us give them same symbol, let it be capital M. This very result is known as, remembered, it is known as reciprocity theorem. Okay, fine. Come on my dears, read this statement of sum number 10. Come on, have you read it? Tell me what is given. We are given two square frames. Both of them are coplanar and concentric. Concentric means having same center. Coplanar means they are arranged in the same plane. Fine. Out of these two frames, one is very large, one is very small. Both of them are square frames. Fine. The side length for bigger frame is capital L and side length for smaller frame is small l. And you can see the condition given to us in the statement is small l is very much smaller than capital L. Fine. We are asked to find out mutual inductance of these two frames. How to find out that mutual inductance? I am showing you. First of all, consider current passing through bigger loop, bigger frame. let it be capital I. And now let us find out the resultant magnetic field produced at the center due to this current passing through all the four sides of a bigger frame. Fine. My dears, you can see this point is equidistant from each side. Okay. So, you are going to get same strength of magnetic field due to each side. Not only that, so far direction of magnetic field is concerned, you are going to get same direction of magnetic field due to each side. And what is the direction I am showing you? This current is right now flowing in clockwise direction. Fine. Then what you should do? You should hold the axis of this frame in your right hand palm such that fingers are taking turn in the direction of current, and in that case the direction shown by the thumb is giving you direction of magnetic field. Right now it is perpendicularly inside. That's why I am putting here very small cross symbols just to indicate inside magnetic field. Okay, magnetic field is perpendicularly inside. Fine. Now first of all, let us find out magnetic field due to only one side. Okay, and whatever is the magnetic field due to one side, that magnetic field we will multiply by 4 in order to get resultant magnetic field at the center point. Fine. Now don't you know magnetic field produced at perpendicular distance y due to limited length of current carrying straight wire? Don't you know that formula? Mu 0 I upon 4 pi y into sin theta 1 plus sin theta 2. Fine. Now tell me, this 4 will cancel, correct? Giving you mu 0 I upon pi into y. What is y? Perpendicular distance. Perpendicular distance of this point from this side is this much. This much means how much? It is half of this side length, half of capital L. So I am writing here L by 2. Fine. So this y is right now L by 2 into, come on, sin theta 1 plus sin theta 2. Theta 1 is also 45 degree, theta 2 is also 45 degree. Fine. How theta 1 and theta 2 are 45 degree each? Very simple. Look, here you just join this point with the two end points of this current carrying straight wire, and now this angle is suppose theta 1, this angle is theta 2. Whatever is this length, same is this length. This is also L by 2, this also is L by 2. So when two sides are equal, opposite angles have to be equal. Opposite to this is this angle, opposite to this is this angle. So these two angles have to be equal. But in this right angle triangle, because one angle is 90 degree, summation of remaining two angles must be 90 degree. And just now you said that both of them are equal. So 90 upon 2, that is 45 degree. Not only theta 1, theta 2 is also similarly 45 degree. That's why I written here theta 1 equals to theta 2 equals to 45 degree. Fine. Now tell me, theta 1 is 45 degree, theta 2 is also 45 degree. Simplify this. You know denominator will become numerator. So 2 mu 0 I upon pi L. Sin 45 is 1 by root 2, sin 45 is 1 by root 2, 1 by root 2 plus 1 by root 2, that is 2 into 1 by root 2, 2 into 1 by root 2. Now 2 upon root 2 will be root 2 in the numerator. So 2 into root 2 into mu 0 I upon pi L. 2 into root 2 into mu 0 I upon pi L. Fine. And now tell me, because this smaller square frame is very small, you can say almost the same magnetic field will persist at each of the points on the cross section of this small frame. Because this frame is very small, you can just consider it as if it is point like. So I mean to say, same strength of magnetic field you can expect at all the points on the cross section of this small frame. Fine. And you know the magnetic flux formula, it is phi equals to AB. That's what I written here, cross section area into magnetic field. But mind well, this is the magnetic flux linked with small frame. So this is the cross section area of small frame. What is the value of B? 2 root 2 mu 0 I upon pi L. 2 root 2 mu 0 I upon pi L. What about cross section area of small frame? It is small L square. You know, for a square, what is the area? Square of side length. and side length for small frame is small l. That's why I am writing here square of side length, which is small l. And now just take this I in the denominator. So you will find out phi upon I. Come on, capital phi upon capital I will be 2 root 2 mu 0 L square upon pi L. 2 root 2 mu 0 L square upon pi L. Mind well, this is the current passing through bigger frame. This is the magnetic flux linked with smaller frame, and you know such a ratio is going to give you mutual inductance of these two frames shown by symbol capital M. Okay. Come on, read now statement of sum number 11. It's a very typical sum. You must understand the figure perfectly. Just read it very carefully. Come on, have you read it? Look, what is given to us? We are given one coaxial cable in which there is a pair of wires which have common axis, and that common axis is this, correct? Lying at the center, this is the central common axis. Here we have thin wire having radius small a, which is surrounded by thicker wire of radius small b. Now tell me from the figure, if this much is b, this much is a, what is this much? This much will be b minus a, b minus a, fine. Suppose current is passed through the coaxial cable, say along axis, that current is passing, say capital I. Now because of that current, say right now vertically downwards, what can be the magnetic field at perpendicular distance x from this axis? You know the formula, B equals to mu 0 I upon 2 pi y. Instead of perpendicular distance y, I am taking perpendicular distance this much, which is x. So instead of y, I am putting here x. As this x will change, this magnetic field will change. So right now magnetic field is a function of x. B as a function of x, it is mu 0 I upon 2 pi x. Okay. If you don't write this x, that will do, but simply don't misunderstand. This is not b into x. No, it's not a product, it's not a multiplication. Simply mathematically we mean to say b is a function of x, that's all. Now tell me, if current is passing this way, in which direction can you expect magnetic field at distance x? In which direction I am showing you? Just consider extremely thin vertical strip, extremely thin vertical strip, and that thin rectangular strip I have chosen here, and that strip has width this much and this much width. This much width is nothing but extremely small increase in the value of x, let it be dx. So width is dx and length is equal to length of coaxial cable, let it be small l, fine. Then what can be the area of this rectangular strip? Area will be, come on, for a rectangle, length into breadth, l into dx, fine. Now what about direction of magnetic field? Just hold this axis in your right hand palm such that thumb should point in the direction of current, this way. Then in that case, in whichever manner the fingers of right hand palm whirl around this axis, in the same manner magnetic field lines also take the turn. So magnetic field lines will take the turn, circular turn this way, okay. And now for this circular magnetic field line, suppose that circular magnetic field line is this, then at this very point, if you want to find direction of magnetic field, then you are supposed to draw a tangent, and the tangent you can draw this way, correct? At this tangent you can see it is coming out perpendicularly, fine. So from this extremely thin strip, magnetic field lines are coming out perpendicularly, coming outside. That's why I am putting so many dots. You know, each dot indicates one magnetic field line which comes out perpendicularly from the plane of the figure. Fine. And because of those magnetic field lines, that strip has got now some magnetic flux. Let us find out that magnetic flux. You know magnetic flux formula, it is magnetic field into area. Magnetic field is this much, mu 0 IE upon 2 pi x. Mu 0 IE upon 2 pi x. What is this cross sectional area? Just now we have found out, come on, L into dx. This is L into dx. And now, let us find out magnetic flux in this much width, correct? In this much width, what can be the magnetic flux? Let us find out. If you want to have total magnetic flux, you are supposed to take summation of partial values of magnetic flux. But now, to take the summation, mathematically what we do, we take normally integration. So let us integrate this partial magnetic flux between these two limits. You know, lower limit of integration is smallest value of variable. Upper limit of integration is biggest value of variable. Right now, what is variable? Variable is x, and its smallest value is this much, equal to a. And biggest value of this variable right now, it is small b. So lower limit is a, upper limit is b. Come on, integration as it is. Come on, d5. What is d5? Mu 0 IE upon 2 pi x into L dx. Mu 0 IE upon 2 pi x into L dx. Fine. Because mu 0 I L upon 2 pi, this much part is constant, I can take it out. Come on, take it out of the symbol of integration. Then left is integration 1 upon x dx. Integration 1 upon x dx from a to b. From a to b. Fine. Now this part as it is. Come on, integration 1 upon x dx. What is it? It is natural log of x. That's what I have written here. Natural log of x from a to b. From a to b. Come on, this part as it is. How you are going to put the limits? You know, upper limit is to be placed first. After putting negative sign, we are supposed to put the lower limit. So instead of x, just write b. After putting minus sign, instead of x, you just write a. Now natural log of b minus natural log of a, it is nothing but natural log of b upon a. Natural log of b upon a. Here it is. Natural log of b upon a. Correct? But now tell me, I have taken this I in the denominator here on the left side. So I will get phi upon I. Phi upon I. Fine. Now this phi upon I, in textbook, wrongly they have taken as self-inductance. Actually speaking, this is not self-inductance, this is mutual inductance, because you are passing current. You are passing current through the thinner cable, thinner wire. And because of that, whatever magnetic field is generated in the surrounding space, because of that you are finding magnetic flux which is associated in the outer part of this wire. And because you are finding magnetic flux associated with outer part, not through this wire, correct? Then current is passing through different wire, magnetic flux is associated through different wire. So you are going to have this ratio known as mutual inductance, not self-inductance. In textbook they have written as self-inductance, that's why here also I am writing capital L, but it is wrong. Whenever correction will come in textbook, at that time you will realize that my argument is very proper. Actually it is not capital L, it is capital M, mutual inductance. Fine. Now read the statement of sum number 12. Come on, read it. What have they talked about? Magnetostatic potential energy density. First of all, try to understand what is this. Look, you are not supposed to draw this figure in the examination. In textbook they have not drawn any figure. Just for your kind knowledge and explanation, I have drawn this figure here. Look, here is the solenoid. and now I just pass current through the winding of that solenoid. And if I am passing current through the winding of the solenoid, you know you are going to get magnetic field inside the solenoid. If this solenoid is very long, then inside magnetic field is nearly uniform, for which magnetic field lines you can show straight, parallel to each other and equidistant from each other. I mean to say perpendicular distance between each two consecutive lines should be same. Now in this magnetic field, in the earlier part of this chapter, we had studied in this magnetic field there is a storage of energy which is called magnetostatic potential energy. Magnetostatic potential energy. And what was that? UB equals to 1 by 2 Li square. 1 by 2 Li square. Remembered? Fine. Now let us find out total volume of this solenoid, because it appears like a cylinder. We take total volume as cross sectional area into length. Now whatever is the volume of the cylinder, same is the volume of this magnetic field, and in this much volume there is this much magnetostatic potential energy. In this much volume there is this much energy, then in a unit volume how much energy is present? Come on, this into this upon this. So it is UB upon capital V. UB upon capital V. What is this? Magnetostatic potential energy stored per unit volume of magnetic field. Such a term, such a physical quantity itself is known as magnetostatic potential energy density, shown by symbol rho B. Fine. UB as it is. What about capital V? Capital V is A into L. Capital V is A into L. Okay, fine. Now just find out, come on, rho B is equal to how much? UB upon A into L. That's what I have started here. Rho B equals to UB upon A into L. Okay. In textbook you will find that this much part they have taken as rho B, but why it is magnetostatic potential energy density, that is what I have explained to you. Now proceed further. 1 upon AL taken side mein, just take it separately, and then UB, what is UB by formula? 1 by 2 Li square. 1 upon 2 AL, 1 upon 2 AL. What about L? What is L? Self-inductance of this solenoid or self-inductance of inductor. In sum number 8 of this chapter, just now we had seen that value of L, I mean formula of L was, capital L was mu 0 n square A upon small l. Mu 0 n square A upon small l into I square. Now this A and A will cancel. So 1 by 2 mu 0 n square upon L into L, that is L square. N square upon L square means what here? N upon L whole square into I square. Now 1 by 2 as it is, mu 0 as it is. What is N upon L? Number of turns per unit length is shown by symbol small n, and it's a square into I square. Correct? Fine. Just multiply numerator and denominator by mu 0. If you do that, then mu 0 to mu 0, what is it? Mu 0 square, and here it will appear 2 mu 0, 2 mu 0. And now tell me, don't you know magnetic field inside extremely long current carrying solenoid? What was the formula? B equals to mu 0 Ni. Just take square on both the sides. B square will be mu 0 square n square I square. B square equals to mu 0 square n square I square. Speak reverse. Mu 0 square n square I square can be replaced by B square upon 2 mu 0 as it is. So this is the final formula for magnetostatic potential energy density, shown by symbol rho B. Fine. Can you recall? You had studied in third semester about electrostatic potential energy density. Electrostatic potential energy density stored in the electric field in the capacitor between the two plates. Remember that formula? That formula was 1 by 2 epsilon 0 is square. Instead of epsilon 0, now we get mu 0. Instead of E square, now we are getting B square. But mind well, epsilon 0 was known as permittivity of vacuum, and here mu 0 is known as permeability of vacuum. This appears in numerator, this appears in denominator. Now tell me, what can be the unit of this potential energy density? What can be the unit? Very simple. After all, it is what? Energy upon volume. Energy upon volume. What is the unit of energy? Joule. Unit of volume is meter cube. Joule upon meter cube. Joule upon meter cube. What is joule? Newton into meter. upon meter cube. Newton into meter upon meter cube. So after all it is Newton upon meter square. And what is Newton upon meter square? It is also called Pascal. It is the unit of pressure, correct? And if it is pressure, then you can write the dimensional formula also, m raised to 1, L raised to -1, T raised to -2. Got it? Thank you.